Space and Science News with James. Today we'll be talking about the mind-bending exoplanet Trappist-1b because why not? Nestled 40 light-years from Earth, this rocky world has been hiding secrets that could revolutionize our understanding of planetary science. Picture a distant planet that defies everything astronomers thought they knew, a world where nothing is as it seems. Recent measurements from the James Webb Space Telescope, JWST, have thrown scientific communities into a state of complete bewilderment. Trappist-1b, once written off as a barren, dead rock, is now teasing the possibility of something extraordinary. Its surface lacks the scars of constant cosmic bombardment, no signs of weathering or cratering typically seen on such planets. Could it be volcanic activity? A concealed atmosphere? Or something we've never even imagined? What's even stranger is the rock itself. Observations suggest it might be impossibly young, potentially as little as 1,000 years old, despite the planet existing for billions of years. How can this be? What processes could explain such an anomaly? Scientists have spent 290 hours of JWST observation time studying this enigmatic world, but answers remain elusive. Trappist-1b's mysteries deepen with every revelation, leaving experts to question the very foundations of planetary science. This isn't just another exoplanet, it's a puzzle that refuses to be solved. As speculation grows and the data pours in, one question looms larger than all the rest: what unimaginable secret is Trappist-1b protecting? Let's dive into the enigma of Trappist-1b and uncover the details that have scientists holding their breath. Trappist-1b, an intriguing exoplanet located 40 light-years from Earth, has long been regarded as a dark, rocky world devoid of an atmosphere. However, recent findings from the James Webb Space Telescope, JWST, are challenging this perception. Observations have revealed a lack of weathering on its surface, signs typically associated with cosmic radiation and meteorite impacts, suggesting that Trappist-1b might be geologically active. This possibility hints at the existence of an atmosphere, potentially rich in carbon dioxide, which could alter our understanding of this enigmatic planet. The Trappist-1 system itself is remarkable, hosting 7 Earth-like planets, 3 of which orbit within the habitable zone where liquid water might exist. Trappist-1b, though closest to its star and outside this zone, remains a subject of intense study due to its unique characteristics. Its proximity to Earth has made it an excellent target for detailed observation, and the JWST has allocated a substantial 290 hours across 10 research programs to unravel the mysteries of these planets. Led by Elsa Ducrot from the Commissariat aux Énergies Atomiques, CEA, in Paris, with contributions from researchers at the Max Planck Institute for Astronomy, MPIA, a groundbreaking study focused on Trappist-1b utilized the JWST's MIRI, mid-infrared imager, to measure the planet's thermal infrared radiation. These measurements provide critical insights into its atmospheric composition, or lack thereof, and surface conditions. The potential discovery of a carbon dioxide-rich atmosphere on Trappist-1b would significantly impact our understanding of planetary evolution around low-mass stars. Such findings could pave the way for re-evaluating the habitability of planets previously dismissed as barren. While Trappist-1b may not host life, the ongoing research highlights the complexity of planetary systems and the importance of modern technology like the JWST in reshaping our cosmic perspective. The findings from the James Webb Space Telescope reveal something astonishing about Trappist-1b. The rock on its surface appears shockingly young, estimated to be no more than 1,000 years old. This revelation directly contradicts the planet's age, which spans billions of years. Such a disparity suggests the presence of dramatic geological processes reshaping the surface, possibly through extreme volcanism or active plate tectonics. These processes could be responsible for the lack of weathering typically expected on a planet exposed to constant cosmic radiation and impacts from space debris. The notion of ongoing geological activity raises tantalizing questions about what might be occurring beneath Trappist-1b's surface. One possibility is that the planet has retained residual heat from its formation, much like Earth. This retained heat could drive a dynamic interior, fueling processes capable of renewing the surface. Another compelling explanation involves the tidal forces exerted by Trappist-1b's central star and its neighboring planets. The gravitational push and pull could create internal friction, generating heat similar to the intense volcanic activity seen on Jupiter's moon Io. What makes this discovery even more intriguing is its implications for the planet's atmosphere, or lack thereof. Geological activity could potentially support an atmosphere, perhaps one rich in carbon dioxide, providing further evidence that Trappist-1b is far from a dead, barren rock. Alternatively, the activity might point to processes so extreme that they strip the atmosphere away as quickly as it forms. Each new piece of data deepens the mystery surrounding Trappist-1b. What drives these processes? How can a planet's surface remain so young in a system billions of years old? These questions remain unanswered, keeping scientists captivated as they dig deeper into the planet's enigmatic story. Trappist-1b's case highlights both the promise and the limits of current astronomical tools. The Haze hypothesis, though intriguing, remains a less likely scenario. Yet, the possibility cannot be entirely ruled out. As scientists continue to refine their methods, the question lingers, could Trappist-1b's secrets be hidden within an atmosphere that defies expectations? Trappist-1b's case highlights both the promise and the limits of current astronomical tools. The Haze hypothesis, though intriguing, remains a less likely scenario. Yet, the possibility cannot be entirely ruled out. As scientists continue to refine their methods, the question lingers, could Trappist-1b's secrets be hidden within an atmosphere that defies expectations? Studying exoplanets like Trappist-1b presents immense challenges, particularly due to the thin atmospheres of rocky planets compared to the thick, easily measurable atmospheres of gas giants. While gas giants produce strong atmospheric signatures, rocky planets like Trappist-1b are far more elusive, requiring innovative techniques and lengthy observation periods. The recent JWST observations of Trappist-1b lasted nearly 48 hours, but even this was insufficient to draw definitive conclusions about the presence or composition of its atmosphere. Astronomers primarily rely on transit spectroscopy to study exoplanet atmospheres. This method involves measuring the dimming of starlight as a planet passes in front of its host star, with specific wavelengths of light being absorbed by atmospheric gases. By analyzing these patterns, researchers can infer the existence and composition of a planet's atmosphere. However, Trappist-1, a cool red dwarf star, complicates this process. Red dwarfs are notoriously active, with large star spots and intense flares that can distort or obscure the measurements. These stellar characteristics pose a significant hurdle to extracting clear data. To overcome these obstacles, researchers have increasingly turned to secondary eclipse measurements as an alternative. This method focuses on observing the thermal infrared light emitted by a planet's heated dayside as it disappears behind its host star. By analyzing the infrared radiation emitted just before and after the planet is eclipsed, astronomers can glean critical information about its surface properties and any potential atmosphere. While this approach avoids the interference caused by the star's activity, it comes with its own challenges. Secondary eclipse measurements are far more time-consuming than transit spectroscopy and require precise alignment of the planetary system to our line of sight. For Trappist-1, the slight inclination of the planetary orbits to our vantage point has proven advantageous. This orientation allows all 7 planets in the system to transit the star, causing measurable dimming and enabling astronomers to gather invaluable data. With Trappist-1b specifically, the JWST's thermal infrared observations have revealed intriguing details about its dayside. However, the limitations of these measurements highlight the need for longer observation times and more refined techniques. Recognizing these challenges, NASA has recently approved an ambitious program called Rocky Worlds, which dedicates 500 hours of JWST observation time to studying the atmospheres of rocky planets around nearby low-mass stars. This program aims to push the boundaries of what we can learn about planets like Trappist-1b. By leveraging secondary eclipse measurements and other advanced techniques, researchers hope to unlock the secrets of these enigmatic worlds, even in the face of red dwarf star activity. Trappist-1b exemplifies both the promise and the difficulty of studying rocky exoplanets. The data gathered so far has expanded our understanding of its surface and atmospheric potential, yet the full picture remains tantalizingly out of reach. Future efforts under programs like Rocky Worlds offer hope for breakthroughs, inching us closer to unraveling the mysteries of planets like Trappist-1b. The study of Trappist-1b offers a glimpse into the rapidly advancing field of exoplanet research, where new technology like the JWST is transforming our ability to probe distant worlds. This ongoing exploration not only challenges long-standing theories but also reveals the immense complexity of determining whether planets beyond our solar system could harbor life or possess unique geological features. Trappist-1b, in particular, has become a focal point for testing innovative methods and pushing the limits of current observational techniques. One of the most promising avenues for understanding Trappist-1b lies in recording its complete orbital phases, a technique designed to provide a more comprehensive view of the planet's characteristics. By capturing data across its entire orbit, including its dark night side when it passes in front of the star and its bright day side as it emerges before being eclipsed, astronomers can create a phase curve that reveals variations in brightness. This phase curve, in turn, offers critical insights into the planet's surface temperature distribution and, potentially, the presence of an atmosphere. The presence or absence of an atmosphere can be inferred by analyzing how heat is distributed across the planet. An atmosphere would act as a medium for heat transport, evening out temperature differences between the scorching day side and the frigid night side. Without an atmosphere, the temperature transition between these two hemispheres would be abrupt and dramatic. Initial measurements of Trappist-1b's thermal distribution have already been carried out, and the results will play a pivotal role in determining the planet's atmospheric status. These efforts underline the broader implications of studying Trappist-1b. The planet serves as a case study for rocky exoplanets orbiting red dwarf stars, a class of planets that could prove crucial in the search for extraterrestrial life. However, the challenges involved, from deciphering subtle temperature gradients to mitigating the effects of stellar activity, highlight just how much remains unknown. Future observations, including those under ambitious programs like NASA's Rocky Worlds, aim to refine our understanding of Trappist-1b. The insights gained will not only shed light on this intriguing exoplanet but also inform the search for atmospheres and habitability on other rocky worlds. As astronomers continue their quest, Trappist-1b stands as a vivid reminder of both the progress and the challenges in the study of distant planets. Each new observation builds on the last, inching closer to answering fundamental questions about the nature of these alien worlds, and, perhaps one day, their potential to support life. Trappist-1b continues to captivate us, revealing a wealth of surprises that push the boundaries of our understanding of rocky exoplanets. Thanks to the groundbreaking observations of the James Webb Space Telescope, this distant world has proven to be more enigmatic than anticipated, reshaping how we think about planetary atmospheres and geological activity. The hints of dynamic processes, whether through potential volcanic activity, heat-driven surface renewal, or a hazy carbon dioxide-rich atmosphere, underscore the intricate and often unpredictable nature of these alien worlds. Such discoveries highlight the incredible complexity of exoplanetary science and reinforce the need for ongoing exploration. Trappist-1b reminds us that the universe is a treasure trove of the unexpected, constantly challenging our assumptions about how planets form, evolve, and interact with their environments. With every breakthrough, we move one step closer to answering the profound questions about whether life could exist elsewhere and what conditions make a planet truly unique. As we look ahead to future observations, particularly through ambitious programs like NASA's Rocky Worlds, we find ourselves on the cusp of even more extraordinary discoveries. These initiatives promise to deepen our understanding of Trappist-1b and other rocky exoplanets, offering a glimpse into their hidden stories and untapped mysteries. Thank you for joining us on this journey through the fascinating world of Trappist-1b. If you're as intrigued as we are by the search for life and the secrets of distant planets, be sure to subscribe to our channel and turn on notifications to stay updated on the latest cosmic revelations. Your curiosity fuels the exploration of the universe, reminding us all to keep looking up, wondering, and exploring the infinite possibilities that lie beyond our sky. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.